Okay guys, so we have some questions I got from section 3.6 from the workbook, the optimization problems. I was looking at, there was no question from 3.5. Uh, I think you guys are doing good. I'm gonna just take some questions from optimization. And I'm sure there will be more problems. You can ask me those questions. And by taking different type of question, you get the idea how to approach the optimization problem. So this is question number 7 on page 67, section 3.6 from the workbook. And the text of this question is here. A cylindrical tank has to be built with no top. The volume has to be 5 pi meter cube. The base of the cylinder is made up of copper and the sides are made up of stainless steel. And the cost of stainless steel is 1/5 the cost of copper, or in other words, the copper sheet is 5 times more expensive than the cost of the stainless steel. So I'm gonna try to break it down. So if you know the shape of a cylinder, if you cut the cylinder open, the sides of the cylinder is made up of a sheet which will have dimensions. One side will be h and the other side will be equal to circumference of the cylinder, which is 2 pi r. Therefore, the surface area of the stainless steel sheet is 2 pi rh. The base of the cylinder is made up of copper. We don't worry about the top, it's open top. Therefore, surface area of the base of the cylinder will be pi r square. Then question says the volume of cylinder is 5 pi meter cube, and the equation for finding the volume of a cylinder is pi r square h, area of the base times height, and this is equal to 5 pi. This equation will help us to write an equation relationship between height and radius of the cylinder. Now then question says the cost of stainless steel is 1/5 the cost of copper, or copper is 5 times the cost of stainless steel. They didn't give us any value for the cost, so some people will start using copper $5 and stainless steel $1, or you can assume $2 for stainless steel per meter square, and then cost of copper sheet will be $10 per meter square. It doesn't matter. I didn't actually even substitute any value. I know C could be anything, so I assume C as the cost of the uh, per meter square for the stainless steel, and then therefore copper will cost me 5C dollars per meter square. Could be in cents, doesn't matter. So that's why I assume C as a constant. Then we have to write the equation for the cost, because the side is made up of stainless steel, and area of the stainless steel is 2 pi r h, and C is the cost. So therefore the cost of the stainless steel needed will be 2 pi r h C. And the base is made up of copper, and area of base is pi r square, and 5C is the cost per meter square of the copper. Therefore, the cost of making this whole cylinder will be 2 pi r hc plus pi r square 5C. Now we have two variables, one is radius, one is height. And remember, any optimization problem we do, we might have many equations in many different variables. Our first goal is to write the equation in terms of one variable, especially now. In future, you will learn how to find the derivative of multivariables too. So we have to eliminate one of the variable. I can eliminate height, I can eliminate radius. So I have already written h in terms of radius, so I can use this to eliminate height. So I use this one, and then I got this equation in terms of uh, the cost in terms of radius only. And then we have to find the derivative of this. When we find derivative and we solve for derivative equal to 0, that will help us to find the optimum value for the dimensions of the cylinder. So I did find the derivative and put equal to 0, and after simplification you can go through my solutions, yeah, how I did solve this. Uh, but if you know the idea of how to find the derivative, you can solve for C prime r equal to 0. And at the end, I got r cube equal to 1. Therefore, the optimum value for radius has to be 1 meter. And we already got the equation between height and radius. Therefore, if I do substitute r equal to 1 and h is equal to 5 over r square equation that we got here, actually we got in the beginning here. So we got the optimum value for height equal to 5 meter. So therefore, the optimum dimensions of the cylinder to have the minimum cost of making the cylinder will be 1 meter as radius and height will be 5 meter. Now see, it's independent of the cost C. Now to make it more clear, I made a graph, and from the graph I can show you it doesn't matter what the C value is. You look here, I have this function. I left the function in terms of the constant C, and I created a variable, means not variable, means the constant value of C can be changing. And I made this x equal to 1 a vertical line to show you that at radius r equal to 1, the optimum dimensions will happen, the optimization will happen when radius is equal to 1. So I even included the point to show the turning point on the graph doesn't change. It will remain at x equal to 1. Actually, y values change, but it doesn't change the x values. So I can play it to show you the cost of the steel C has to be positive. I just start from 0.1 and I could be going to 2. I can have 200, 300, 400, whatever, but can't be negative. So I didn't start from 0. We can't have 0. So I did start from, let's say, 10 cents per meter square for the steel. So let's play it. You notice the optimum values always happen at x equal to 1. That means radius always has to be 1 for any cost of the stainless steel. So variable value for C, but only positive value. So I think this is more clear uh, to explain the idea. Okay, so that's this question, and I'm gonna take one more question in my second video, another optimization problem. So you can see once more, I can go back here to see how did I start, and then how I come up with the equation, how I eliminate h from the equation, and then I wrote the equation for the cost of this cylinder in terms of radius, and then find the derivative, and we solve for C prime r equal to 0 to find the optimum radius and height.